Based on the above rules, an autonomous system may know about a lot of IP prefixes. This is a big set, and when it is exporting, it may export only a subset of these IP prefixes. And let's look at one specific IP prefix that it has exported. The same logic will apply to other IP prefixes as well. So when it export this particular IP prefix, it is basically telling that this particular prefix I can provide a path to. That is what it is telling. Now once this AS2 receives this particular IP prefix, then again it will apply its own rule, and let's again say it also decided to export this. So it is now going to tell AS3 that I can provide a path to this particular IP prefix P. Now the routing that is employed as part of this advertisement process is path vector routing, which we briefly mentioned when we covered distance vector. So basically AS2 will advertise I can reach P via AS1, AS2. Similarly, AS4, when it receives this advertisement, it will note that I can reach P via AS1, AS4, and it is going to advertise this. Now suppose AS2 decided that it wants to reach prefix P via this path, and when it were to advertise this, the vector that it is going to generate is P I am going to reach via this. And this vector, it is going to advertise it to its neighbors. Let's say it came to AS1 as well as AS3. Now AS1, since it sees itself within this, it is not going to act on this particular information because it's there as part of the path. So this is how you avoid looping as part of this routing process. So to facilitate this kind of path vector routing, each autonomous system is assigned a unique number, which is a 16-bit number, by a central authority. The fact that we are using path vector, it prevents routing, and this path vector can also permit policy-based routing. For example, if AS1 saw two paths, one let's say via AS2, AS3 to some destination D, and another via AS2, AS4, AS5 to the same destination D, and if AS3 were its competitor and it doesn't want to send, even though this is kind of relatively short, you don't really know because you don't know how many internal routers it is passing through, it will not select this path, it will select this path. Now let's all put it together, integrating this intra and inter-domain routing. So again here I have shown a particular autonomous system which has border gateway routers A, C and F, and based on this eBGP sessions, this border gateway routers have heard about prefixes, and they also found out what is the path to take to reach these prefixes. For example, it may have heard about this prefix from multiple border gateway routers, but based on, let's say, whatever policy it has, it will, let's say it has decided this over this. So that and all, it figures out internally what to do about that. Now, whatever information they have figured out, what they do is they established iBGP sessions to each of these routers and convey this information. By the way, the iBGP session between A and D, while I represent like this is a logical view, whereas internally when it goes from here to here, it actually passes over the router P. But since I said it is a TCP connection, this iBGP sessions, internally the routing between A and D is handled by the interior gateway protocol. We don't have to worry about it. Now based on this iBGP sessions, all the routers within this particular autonomous system have this BGP table for the autonomous system. So they know that to reach this you have to go via A, to go reach this you have to again go via A, to reach this you have to go via C, and to reach this you have to go via F. So this information is consistent across all the routers, and this consistency was achieved by the iBGP sessions. Now let's look at this specific router B. This specific router has an interior gateway table. This must have been gotten either through RIP or OSPF, and this is saying how to reach the different routers. What is the next hop to take? Combining these both is where you arrive at the forwarding table at router B. You know that to reach this particular IP prefix, you have to send it to this border gateway router, and to reach this border gateway router, you need to go through this. So you go in here. So here again, it's the same. Let's look at this specific case. So 10.0.0.8, the next BGP hop is this, but to reach this C, your internal gateway is saying you have to go through D, thereby to reach this prefix, you send it to D. So this is how you integrate intra and inter-domain routing. So why do we have inter and intra-domain routing? For various reasons. One is policy, where ISPs want control over how their traffic is routed, and if you want policy, you need to go for inter-domain routing. But within an autonomous system, there is no policy decisions because everything is being controlled by a single administration. There you can focus on performance. So that is what this is saying. As far as inter-domain is concerned, policy dominates performance, whereas intra-domain is concerned, one can focus on performance. And scale is again handled via imposing an additional hierarchy via separating out inter and intra-domain routing. For example, if you're doing link state routing as part of the intra-domain routing, you're not really flooding your packets across autonomous systems. It is contained within your own autonomous system, so it scales well. These border gateway routers will summarize that information and pump it into the other autonomous systems via the inter-domain routing. Now the complexity of the exterior gateway protocol, that is employing path vector, is roughly of the order of the number of autonomous systems. There will only be a few border gateway routers per autonomous systems, and the number of autonomous systems themselves are not going to be that many. So this complexity is also easily handled. And when you look at the interior gateway protocol, the complexities will be roughly of the order of the number of networks within the single autonomous systems. Because often a router has to interconnect one or two of these networks. So by splitting the routing into inter and intra, one could handle policy, performance to some extent, and scale. So to summarize, the internet architecture is very complex with different relations between the ISPs, and this tends to complicate routing. We saw that this complexity can be handled via inter and intra-domain routing, where policy dominates the inter-domain routing. The protocol that facilitates inter-domain routing is the BGP protocol. This is common across all the autonomous systems, and this is managed via eBGP and iBGP sessions. How you export, how you import rules, all these are based on the relationship between the ISPs, and we also saw how the intra and inter-domain routing work together to build forwarding tables. A big round of applause. We have finished network layer.